Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover the first derivative test today. Now, first derivative test talks about how the derivative relates to, how the function increases and decreases. So what we have is if f prime of x is greater than 0 for all x on interval I, then f is said to be increasing on I. And similarly, if its derivative is less than 0 for all x on an interval I, then f is said to be decreasing on I. So what I've done is I've drawn a graph right here, and what we've practiced before this is finding critical points, and let's call this value C1 and let's call this value C2 for critical point 1 and critical point 2. And I know that these are critical points because when I look at its derivative, they're going to be horizontal, which means that the slope of these tangent lines are going to be equal to 0. So really what I can say in those cases is f prime of C1, also equals f prime of C2. Both of these things are equal to 0. So what this does is this separates it into intervals, broken up by our critical points. So what I can have is, if I'm looking at the x-axis or the domain of this thing, I'm going to have some C1 and I'm going to have some C2. Now the function is going to be monotonic on intervals cut by these critical values, and what I mean by monotonic is it means the function is always going to be increasing or the function is always going to be decreasing on those particular intervals. So kind of in between these things, you can see between C1 and C2, since the derivative is equal to 0 at C1 and also C2, that this function is always decreasing on this particular interval. It'll either do one or the other. It cannot do both, because the only time it's going to change from increasing to decreasing is when it switches from negative to positive, which means it's got to be 0 at a particular spot there. So then you can see beyond C2 this function is monotonic, but in this case monotonic increasing. And I've done an endpoint here, and sometimes we have to be careful of these endpoints as well. But regardless, that this starts at some a and it goes on forever. So the domain of this particular function is going to be from a to infinity. But we can see also below C1 that this thing is monotonic increasing. So it increases before the critical point. It's going to decrease after that first critical point, and then increase after that last critical point. Now, a function is going to have a maximum, or we'd say a local maximum. F will have a local max if, this we can tell that this is a local maximum at C1 if the function increases before C1 and then decreases after C1. So we can say if it's increasing before C1, the critical value, and then decreasing after. And then very similar, we can change this to say f will have a local minimum if it goes the other way. If it decreases before and increases after. So if decreasing for a critical value, and increasing after. So this is going to be the basis of how we're going to find these local mins and local maxes. Now be careful. A is an endpoint in this particular case. So just like we did with closed intervals, endpoints can also be local mins and local maxes. And we can see in this case, since it's increasing after that, after that endpoint of A, that A has to be a local minimum. And then similarly, if this ended at a spot, this would have to be some local max if I had some endpoint, if it's increasing to that endpoint. All right, so let's go through the examples and practice this technique of finding critical values. We'll determine if it's increasing or decreasing. Let's make sure that this is kind of clear. So what we know is from A to C1, we can see that this function is increasing. From C1 to C2, we can see that this function is decreasing. And then from C2 on, this thing is going to be increasing. So we can say if it goes increasing first, decreasing second, that means it's got to be a local maximum. If it goes decreasing first, increasing second, that means it's got to be a local minimum. So this is going to be the technique that we're going to be using to, locate these maximums and these local maxes and local minimums. And that's mostly what they're asking for. They're not asking for the max or the min themselves. They don't really want to know the output. They just want to know the locations for which these things happen. So we're going to determine local extrema of three examples. I'm going to do a polynomial, I'm going to do a rational, and then I'm going to do a radical. Okay, so first, start out with this quadratic. It's a really good place to begin. The first thing we're going to have to do is we have to find critical values. So let's find our critical values, or we'll call them critical points. And remember, this happens when f prime of x is equal to 0. Now we also separate these things at places where f prime would be undefined, even though they're technically not a critical value always. You could have something that looks like this, like an absolute value function. It does have a critical value there, even though its derivative is not defined. We also know that the function will be undefined at some kind of asymptote. So things we have to be careful of is, the function might decrease before the asymptote and then increase after. So, where the derivative is undefined also is places I'm gonna cut the domain of the function so that I can determine it increasing and decreasing. But sometimes they're not extrema because they're an asymptote, and sometimes they are. So just being conscious of when this thing is undefined as well. Okay, so in this case it's a polynomial. It's defined everywhere, so that's not really the problem in this case. So f prime of x, well, its derivative is going to be 2x minus 8, and we know we have to set this thing equal to 0. So then I'll factor out a 2, I get x minus 4 is equal to 0, and then divide both sides by 2, or 2 is never 0, so the only solution is going to be when x equals 4. So now what we're going to do is we're going to look at the monotonic intervals. So the way we're going to pull that off is, we're going to have some axis right here, and it's going to, that's horrible, and it's going to be cut at, it's going to be cut at 4. So, from these intervals, what I know is that, this is going to be that critical value of x is equal to 4, which means, this is the only spot where the derivative is equal to 0, so, either before is going to be always increasing, or before it's going to be always decreasing, and this will always be increasing. So the only spot it's going to switch from increasing to decreasing or decreasing to increasing is going to be at that particular value there. So in order to determine if it's increasing or decreasing here, we have to pick an x value, and then we're going to plug that into its derivative, and then figure out if it's increasing or decreasing really just by checking the sign of this particular value. So let's find a candidate here. I don't know, I'm going to pick a 0 because it's a very easy number to work with, and that's below 4. And over here, maybe I'll just pick 5. Now, I'm not choosing exactly the same side of 4 or the distance from 4 because it shouldn't matter. Any number I pick in here, this interval will always be increasing or decreasing regardless of the number that we pick. So you might as well pick easy ones. All right, so when x is equal to 0, also when x is equal to 5, I'm going to plug these things into the derivative. So the derivative is going to be equal to, 0 squared, sorry, that's not right. It's going to be the derivative, which is right here. This is going to be 2 times 0 minus 8. So this is going to equal negative 8. And for the derivative here, this is going to be 2 times 5 minus 8. So 10 minus 8 is going to be equal to 2. Now what I know is that negative 8 is less than 0 and 2 is greater than 0. So a lot of times we say, this is negative and this is positive, meaning less than 0. Positive meaning greater than equal to 0. So what I know is that, this thing is decreasing before, and then is increasing after. So, this interval here is decreasing for the entire values from 0 to 4, and also increasing for all the values from 4 beyond. Again, it won't matter what number we pick. Plug in 2. 2 times 6 minus 8 is still going to be, a positive 4. It's still going to be greater than 0. It shouldn't matter what number you're picking here. They're always going to be bigger than or equal to 0. It won't matter what number I pick in here. They're always going to be less than, so not equal, but less than 0, greater than 0. Equal 0 is only that spot. All right, so what we know is it decreases before and then it increases after. So a lot of times I have my students like, okay, decreasing before, increasing after, got to be a local minimum. So that means x equals 4, since it's, it's decreasing first and then increasing after. X equals 4 is going to be, the location of our local min. Now, it has no local maximum because, it's going to increase forever in this direction. It's going to also, it's decreasing, which means it came from infinity from this direction, and then it's increasing, which means it comes from, goes to infinity in that direction. So there are no local maximum because the function looks like this. All right. Now, let's make it a little more challenging. What about a rational? All right, very similar. All right, very similar. Regardless if we're given a rational or a polynomial or a radical, the first thing we're going to look at is we're going to look at critical values, and this is when f prime of x is equal to 0. So critical points. F prime of x is equal to 0, or when it's undefined. Now, again, they're not guaranteed to be critical points, but they could be asymptotes or they could be sharp points, so they could be max or mins. We just have to pay attention to what they are. And we'll look at the domain of this function after to figure out what this thing is. A lot of times the book will actually say, everything except, x is not allowed to be 2, because what we know is the function you can't divide by 0, so x can't be equal to 2, so that means the domain goes from negative infinity to 2 and 2 to infinity, really just kind of verifying that, 2 is an asymptote. Okay, so the derivative. This is a quotient, therefore I have to use a quotient rule. So derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. Remember, this has to be equal to 0. Now, simplifying the top, we have a 2x squared minus 4x, and then minus x squared plus 3 all over my x minus 2 squared. So then 2x squared minus x squared is going to be x squared minus 4x plus 3, and the bottom is going to be x minus 2 squared. Now remember, we're asking when this thing is equal to 0, and a fraction is going to be equal to 0 when its numerator is equal to 0, because I'm going to multiply both sides by the denominator. So x squared minus 4x plus 3 is equal to 0 times x is 2 squared, which means this will just spit out 0. And then factoring this, I'm going to get a x minus 3, x minus 1 is equal to 0. So what I have is critical values of x is equal to 3 and also x is equal to 1. So those are my critical values. Let's do them in order. Critical values are critical points. So now when we look at the monotonic intervals, so far we know that we are cutting at x is equal to 1 and also at x is equal to 3. Now I also care about where this thing is undefined. It might not change from increasing to decreasing, but it might. So let's just pay attention to that. Well, this thing will be undefined when the denominator is equal to 0. So this is when x minus 2 squared is equal to 0. Or x minus 2 is equal to the square root of 0, which is still 0, so x is equal to 2. So I'm also going to cut this at 2 because I also know that, remember, it has an asymptote at 2. So it makes sense that its derivative is not defined there if the function is not defined there. All right, so now when looking at these intervals, this interval goes from, minus infinity to 1. This is going to be from 1 to 2. This interval is going to go from 2 to 3. And this interval is going to go from 3 to infinity. And I really just need to know, is it increasing or decreasing, increasing or decreasing, increasing or decreasing, and so on. Okay, so what I have to do is I have to pick an x value in this particular interval, and I'm going to plug that into the derivative and see if it's greater than or less than 0. So I'm picking an x value, and here, every time I can pick 0, I sure will. Here I'm going to pick 1.5. Here I'm going to pick 2.5. And here I'm going to pick 4. Again, it doesn't matter. Just got to pick a number in there. All right, so x is equal to 0. So 0, 1.5, 2.5, and 4. And then I'm going to have to plug these into this derivative, which is this piece right here. So this is going to be equal to, I'm gonna do it in factored form. We know that that this thing looks like this. So this is x minus 3, x minus 1, all over x minus 2 squared. Might be easier to do it there. All right, so we're going to have 0 minus 3, 0 minus 1, all over 0 minus 2 squared. So we're going to have negative 3 times negative 1 will be 3, all over negative 2 squared. Negative 2 times negative 2 is positive 4. So this is greater than 0. Similarly, we have a 1.5 minus 3, and then I have 1.5 minus 1, all over 1.5 minus 2 squared. Actually, I have these written down. I'll do them again. So this actually gives us a negative 3, which is less than 0. This one also will give us, negative 3, which is less than 0. And then when I plug in 4, I'll write this. I'm just out of room here. So 4 minus 3, this is 4 minus 1, all over 4 minus 2 squared. And 1 times 3 is 3 divided by 2 squared. Gives us 3/4 as well, which is greater than 0. All right, so this is positive, therefore it's increasing. This is negative, this is negative, this is positive. Let's put these in different colors. So this is increasing. This is decreasing. This is decreasing. It did not change at the asymptote, and this is increasing. Remember, they sometimes can. So again, it decreases on this interval. It increases on this interval. It decreases on this interval, and then it, sorry, I did that wrong. This is decreasing. I got them all wrong. Increasing, decreasing, there we go, decreasing, and then increasing. So increasing, decreasing, decreasing, increasing. Okay, so what we know is, and I kind of do like the hand thing, so it's increasing here, it's decreasing here. That means that x equals 1 has to be a local max. Its location. If you want to find what the maximum is, you're going to have to plug 1 back into the original function. And then similar, this thing goes from decreasing first and then increasing after, which means x equals 3 has to be a local minimum. Again, if you want to find that minimum value, you'll have to plug 3 into the original function to find its output. But a lot of times the questions are asking, where are their locations, not exactly where are the values. All right, last one. All right, so in order to do this, we're going to have to find critical points, and we know that critical points happen. Critical points happen when, f prime of x is equal to 0, or we'd say undefined. Not sure if that's useful here, but we'll kind of, it kind of is. We'll see why in a second here. All right, so in order to find the derivative, this is a product, so we have the product rule. So we know this is x squared times 5 minus x to the 1/2. Maybe easier to take the derivative that way. So derivative of the first times the second plus the first times the derivative of the second, so 1/2 times 5 minus x to the minus 1/2 times the derivative of what's inside, which is going to be a -1. All right, now cleaning this up, I have 2x root 5 minus x, and then cleaning this one up, we're going to have a minus x squared all over 2 times the square root of 5 minus x. Remember, we're setting this bad boy equal to 0, or undefined, and we'll get there in a minute here. All right, so in order to really answer this question, it'd be a lot easier if I wrote them with a common denominator. So what I'm going to do is I'm going to multiply top and bottom by 2 times the square root of 5 minus x, 2 times the square root of 5 minus x, just to this, to the first term. And when I do that, I'm going to get 4x, and then root 5 minus x times 5 minus x is going to be 5 minus x all over that common denominator. And then minus, x squared over that common denominator. And then cleaning this up, this is going to be 20x minus 4x squared minus another x squared all over that common denominator. So this is 5 minus x equal to 0. So we're going to get 20x minus 5x squared all over 2 times the square root of 5 minus x. And it'll likely be easier if we factor the top, so I can figure out when the numerator is equal to 0. So factor out 5x, I'm left with 4 minus x. And on the bottom, this is 2 times the square root of 5 minus x. Now, when this is equal to 0 is when the numerator is equal to 0. So clearly when, let's do these in blue, I like the critical values. So x equals 0, that comes from that one. And then x equals 4, that'll come from that factor. Now, undefined. This undefined part, remember that I have a radical. The bottom can't be equal to 0, so clearly x can't be 5. So x is not allowed to be 5, because 5 minus 5 would be equal to the square root of 0, which would be 0. But moreover, we know that 5 minus x has to be greater than or equal to 0. I got rid of the 0. So technically, if it's on the bottom, you can just say greater than 0. So this is when 5 is greater than x. Or x is less than or equal to 5. Now again, I've already excluded the 5, so really what we'd say is the intersection of these two things is just when x is less than 5. All right. I'm still going to leave the 5 in there because 5 is defined for the function. It's just undefined for the derivative, and we will see what that means in our critical values, okay? So, or our intervals. So here's our intervals. I'm going to slice this at 0. We're going to slice this at 4, and then we're also going to slice this at 5. Remember, 5 is part of the domain. The domain of this thing is, the domain would be when 5 minus x is greater or equal to 0. So this is, solving this is when x is less than or equal to 5. We just did it here. So I know that 5 is included in the original function, even though it's undefined and its derivative. I'll explain why graphically in a minute. Okay, so our intervals. We're going to go from minus infinity to 0. We're going to go from 0 to 4. We're going to go from 4 to 5. And if you miss this, you might try to go from 5 to infinity and see what happens. So I know it's not part of the domain, but I'd like to kind of talk about it. So when we pick our x values, and we're going to plug these things into the derivative, I know I have to pick an x value in here. Let's go -1. Let's pick an x value in here. Let's go 1. Let's pick one in here, which is 4.5. And also if you want to pick like 6 in here and kind of talk about what happens. So, pick an x is equal to -1, x is equal to 1, we have 4.5, and then we'll also plug in 6. And these have to go into the derivative. So, again, plugging into the derivative is going to be equal to, 20 times -1 minus 5 times -1 squared, all over 2 times the square root of 5 minus, -1. Just, using this, or you can use this one, it's up to your choice here. So when we plug in -1, what I get is, let's make sure that looks right. Just double checking, and it says we're good. So this is, minus 5.1. When I plug in x is equal to 1, I'm going to do it down here. I'm just kind of out of room here. So when I plug in x equals 1, I'm going to get, so I'm going to get positive 3.75. Plug in 4.5 in. We get negative 7.95. That's what it would be. Negative 7.95. And then when I plug in 6, to make me feel good about myself, to show that this is undefined here, 6, enter. Plus I. Nice. This calculator is impressive. It's got some strange stuff in here. So, this is undefined, so you get kind of some error, so we know that, we're not going to get an answer there. Because remember that the function is undefined there, therefore, so it's its derivative. All right, so what we have here is this thing is less than 0. This is greater than 0. This is less than 0. So what we have is being less than 0 means that we're decreasing. Its derivative is less than 0. This derivative is increasing. The function is increasing because the derivative is bigger than 0. And then it's decreasing because the derivative is less than 0. So again, I should have did this in red. Oh well. So this is, decreasing. This is increasing. This is decreasing. So what we know is it's decreasing first, increasing second, which means x equals 0 is a local min. Similar, it's increasing first and decreasing second, which means x equals 4, right here, is going to be a local max. Now remember that the function is defined there, just like the function is defined at all these points. Its derivative is not defined there, but the function is defined there, so you're allowed to be equal to 5. So if it decreases to 5, it also means, I have an endpoint here, which means x equals 5 is a local min. So really be careful of your radical functions because they tend to have endpoints. This only has one endpoint, but if it's quadratic inside, it would have 2 endpoints. So really what we have here graphically is the function is going to look something like this. We had a local min first, local max second, local min, and then it goes off into infinity. We can see that this domain goes from minus infinity to 5. So minus infinity to 5, this being 0, this being 4, this being 5. So that's why it looks like local min, local max, local min, because it's an endpoint. So if you like the content, please subscribe.